Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in the University of Helsinki in Finland, where I study cosmology. So that means that I study the universe, the contents of the universe, how things evolve, how things interact, all of the cool stuff happening inside the universe. It's a great topic. I really enjoy being a cosmologist. It's great fun to be able to just stare out in space and go like, I know what you did there. Most of the time we don't know what the universe did, but we're trying to figure it out, and that is fun. And I love chatting to everyone about cosmology and about science and about all of the cool things I get to work on. Hey, David Dunn, Happy New Year to you as well. Thanks for joining. So Happy New Year to everyone if you've already celebrated New Year, if you're in a Western calendar. And welcome to the first Cup of Cosmology of 2023 or of 12,023, depending on your frame of reference. It's great to be here. As I was saying, I love chatting about science. I love chatting about cosmology. I love chatting to everyone about all of the cool things happening inside the universe and all of the stuff I get to work on. So Cup of Cosmology is an interactive stream. The idea here is that you can ask me anything you want, and I will do my best to try to answer. I don't have all the answers. Oftentimes I will not have the answer to the question, and then we can either figure it out as we go or shelve it for future discussion. But do feel free to ask me anything. This is an interactive stream. Anything you've ever wanted to know about space, about cosmology, about dark matter, about gravitational waves, this is your chance to ask this today, and like every week here on Cup of Cosmology. It's not a limited time offer. You get to come and chat to me anytime you want. Hey Scott, hey James, great to see you in the chat as well. And don't worry, Scott, you're not late. 2 minutes in. The first 2 minutes, it's just me rambling and setting the scene anyway. Looking forward to finding dark matter this year. Yeah, that would be nice, right? If we could find dark matter this year. Hey Paul, hey Ange, great to see you. So many regulars here. Always great to see you. Let's enjoy our first cup of cosmology as much as our first great cup of coffee for the year. Yes, let's go into this with energy and positivity and good vibes. Yeah, so as I was saying, welcome back to all the regulars. Welcome to any first-time viewers. If you're new here, welcome. If you haven't done so already, please do subscribe to the YouTube channel here, leave a comment, like the video, do all of the usual YouTube things. It really does help boost my reach. The YouTube algorithm learns and sends my videos out, and I get more visibility if you press all of the right buttons. So please do like, subscribe, leave a comment, all of the usual stuff. It really does help, and I really do appreciate it, especially as I've had to move platform a few times over the last few years. So it is appreciated to build up the audience again. So what's the deal with Quiz-Kazakh adding 10,000 years to the calendar? That's a great question, Scott. So I made the offhand comment of it could be 12,023, depending on your frame of reference. This is what Quiz-Kazakh, the science outreach channel on YouTube, does, where they decided that a more fair way of counting years is, rather than pinning it to one specific culture or one specific religion, pinning our calendar to the time at which humans first began to write things down, because that's a way where you can really transfer knowledge. Of course, you can transfer knowledge spoken as well, but once you start writing things down, it's a way of keeping history more, or at least keeping historical records. Whether they're accurate or not is another question. So rather than pinning the calendar to a specific culture, Quiz-Kazakh decided the fair way of doing it is adding about 10,000 years, and then you pin it approximately to the time when we started developing writing. Of course, this is also kind of arbitrary, but it's a thing that they've kept going now. And if you get the Quiz-Kazakh calendars, instead of saying 2023, it will say 12,023. Just add on 10,000 years, and then it's also easy to remember. But whatever frame of reference you're using, if you're in a new year, Happy New Year. If you're not in a new year, I hope you're enjoying your year, regardless of what year it is for you. So, as this is the first stream going into the new year, I want to give going into 2023, I want to give some outlook as to what we can expect in cosmology this year, because there are quite a few things happening. There's always going to be unpredictable things in cosmology, or results that I don't know are coming, or that nobody knows are coming. There's things under lock that nobody knows about officially. There's the rumors that we hear, but nothing official. But then there's stuff that is expected to happen. And we have a series of telescopes or experiments that are expected to either give us new data or start doing cool stuff this year. So there is a lot of stuff to look forward to in in the coming 12 months in cosmology in general. So I want to just give an overview as to what to expect. And of course, there will be unexpected things, there will be news, there will be developments. Maybe we wake up one day and someone's found dark matter. That would be pretty cool. I doubt it, but you never know. Would be pretty cool. So there's going to be unexpected stuff, and anytime there's a breaking cosmology story, you can come on to Cup of Cosmology to hear all the details, assuming I have time to both read the news and prepare the topic. So, as always, feel free to ask me any questions. If you want to take me off topic, go ahead. If you want to distract me with puns, that's the easiest way to derail the conversation. So because 0 means 0, you count this year as 13 billion. Yeah, the problem there is we have the uncertainty. The age of the universe is 13.82 billion years, but then we don't know the rest of the digits, right? So then it's quite hard to add on 2000 to something that is 13.82 billion plus minus half a billion. So it gets a bit hard to count from the start of the universe. And then there's the whole thing that how do you define the start of the universe? That's another big and interesting question we have. So yeah, before jumping into what to expect this year, I want to review a few things of what are the current open challenges in cosmology. So what are the things that we really hope to address or that we're still unsure about? So where is cosmology currently? I'm going to start by just very, very quickly reminding you of what we do know, and then I'm going to move into everything we don't know. So the universe, as far as we know, is made up of three main components. Everything you see, everything you interact with, everything from the stars at the night sky to me, to my tea, all of this is normal matter. And normal matter only accounts for 4.9% of the energy budget of the observable universe. Then there's another big chunk of the universe that is in the form of dark matter. Dark matter accounts for 26.2% of the energy budget of the universe. And dark matter is this weird type of matter that interacts via the gravitational force, but doesn't interact via the electromagnetic force. This means that dark matter is basically invisible. Light does not interact with dark matter, as far as we know. Dark matter does not absorb light, it does not reflect light, it does not emit light, which makes it very, very difficult to be able to measure it when we can't actually see it. And the remaining 68.9% of the energy budget of the universe is in the form of dark energy. Now, dark energy is this weird type of energy that is pushing everything outwards. It acts like an anti-gravity kind of thing. It pushes things away from each other. It's driving the accelerated expansion of the universe. And that's pretty much everything we know about dark energy. This is the standard paradigm in cosmology currently. This is a standard cosmological model, whereby the universe is made up mainly of dark energy, dark matter, and a small amount of normal matter. And this is fun because I say I'm a cosmologist. My job is to study the universe. And based on this pie chart I've just shown you, that we only actually can really study 4.9, or we can only see 4.9% of the universe. The rest is dark and mysterious and quite difficult to study, and we're still trying to figure it out. But we do know some things about dark matter and dark energy, even if we haven't been able to figure things out entirely. So from here, we can see that one of the big questions in the field is, what is dark matter? What is dark energy? These are questions that I don't think we'll get the answer to tomorrow, but we can make progress in this direction, and there's going to be a lot of stuff helping us out. We know some things about dark matter. We know that it attracts other things. We have approximate ideas on the masses. Like there's 80 orders of magnitude, but we know if dark matter is too small, it would travel almost at the speed of light, and then structures couldn't form. If dark matter is, on the other hand, really, really, really massive, we should have seen it. So dark matter is probably particles or a swarm of something, or it could be primordial black holes, but we have an approximate range as to how big a clump of dark matter can be, we think. We know that dark matter doesn't really interact with much. It doesn't bump into many of our normal particles, to the best of our knowledge. So there are some things we know, and we've been able to eliminate a lot of possibilities for dark matter. As for dark energy, we also know overall what it does. We know what it's doing to the universe. It's driving the accelerated expansion. How it does that, why it does it, what is dark energy? These are questions that we're still trying to figure out the answer to. So one of the biggest questions in cosmology is, what is dark matter? What is dark energy? These are very, very, very cool questions. I was going to catch up on the comments in a minute. For fast-traveling particle, would the universe be a lot younger because of relativity? Excellent comment there, Paul. And the answer is yes, time is relative. Depending on how fast you're moving, time passes at a different rate. This is something we know from Einstein's relativity. If you move almost at the speed of light, time will practically slow down. For an outside observer, you will still feel yourself experiencing time the same way, but an outside observer would see your clock ticking slower. So then it's quite hard to find an absolute frame of reference. However, you can try to remove any movement within the universe and from there calculate the age of the universe. When you use the CMB, for an example, you can subtract the motion of the Milky Way through the universe. You can subtract our motion around the Milky Way. And then once you subtract that, you're left with the cosmic microwave background radiation, this background noise, which is approximately the same in every direction. And this is something that really allows us to get kind of a frame of reference where we can extract the age of the universe. So I just threw out a jargon thing there without explaining it. CMB, cosmic microwave background radiation, 11 minutes, 39 seconds today before the amazing image appeared. This is the oldest light we can see in the universe in any direction we look. This is a snapshot of what the universe looked like in its infancy. And this is what you see at the back of everything, behind everything else in the universe. When you actually take the observations of the CMB, you see things are slightly redshifted based on our motion. But once you subtract away our motion, you're left with this kind of absolute frame. And here you can calculate the age of the universe. And then the idea here is that anyone else could calculate the age of the universe in the same way, subtracting their motion. So then when we say the age of the universe is about 13.82 billion years, we think that that's no longer subject to your motion because we've tried to subtract all motions that we know of from the image. So it is a great point. It is a great question, Paul. But technically, when we measure the age of the universe, we can do this in a way where we subtract the motion, or our own motion from, we remove ourselves from the equation as best we can when we are part of the system we are observing. Okay, a few more questions. I see lots of cool questions today. If photons don't experience time at all, is it still the beginning of time for them? This is an excellent philosophical question here. Now, going back to this idea that time is relative, photons travel at the speed of light. Now, as you approach the speed of light, as I was saying, from an outside perspective, your clocks tick slower. So if a photon, a particle of light, were carrying a clock and you were able to measure that clock, you would not see it moving. It would be still, which means from an outside perspective, that photon does not experience time. But then we talk about photons experiencing time. What do photons actually experience? They are inanimate particles after all. So then it becomes very weird of, is time actually something you can attribute to a moving particle, or is it our way of understanding the universe? You can use entropy, how much chaos there is in the universe, to kind of construct what time is. But then the question of, does something experience time, is an odd question, and one that we get much more into the realm of philosophy than trying to answer this with physics. But it is a very, very, very cool question. Calling it normal matter is an insult to the other 95% of the universe. Yes, but we call it normal matter because it's what we're used to. You know, we're made up of it. It's what we can interact with. It's what we can see. It's what we knew first. So it's what we call normal matter. In more jargon terms, we often refer to it as baryonic matter because it's made up of baryons. And baryons is just a way of saying particles in the standard model that come together in specific ways. So you can call it baryonic matter if you want a slightly more jargony word, but normal matter is the word we normally use for it. And yes, it is not really fair given that there is a lot more dark matter and dark energy than normal matter. Primordial black holes came up yesterday along with Hawking radiation. Would a very small black hole explode in an extremely energetic event, and why? That is an interesting question. I'm going to make a note of that and come back to that, Scott, because I want to think about that before answering. I'm just making a comment here on this, because I saw there were also some comments kind of related to what we're just saying here about photons experience loneliness. We don't know what photons experience. It's always a fun thing of how do we attribute an experience to a particle. Comment from James, still perplexed when I hear that light is also a particle, also wondering if this means that all waves have mass. This is an excellent point here, James. So light is a particle and a wave. We know that every particle has a waveform as well, and it can behave either as a wave or as a particle, depending on what it's doing. Now, in the case of light, photons are actually massless. They do not have mass. The particles of light, photons, do not have mass. So in that sense, the electromagnetic waves, which are the waves associated with the photons, do not carry mass themselves because they are not massive. But then you can have other waves that do carry mass, like gravitational waves carry energy away from the origin. Do they carry mass energy? But yes, when you break everything down to a quantum level, you can have particles can behave as a particle and as a wave. And this is something that we have been able to verify in several different quantum mechanics experiments. You can set up quantum physics experiments where you can see that if you observe a particle, sometimes it behaves as a particle. If you don't observe it, it behaves as a wave. It's a very cool experiment to do. It's something that we just kind of have to accept that when you break it down to the quantum level, you can have things that act as particles and things that act as waves. So it's very cool, very cool. I see the question here about experiments to find dark matter, and I'm very glad you asked. We are going to discuss this today. Not right now, but we are going to discuss this today. I'm just noting it, and if you stay with us, we will answer that at some point today. I say we as if I'm multiple people, still only one personality to my knowledge. Since big black holes slowly evaporate, I think they would be very small black holes by the time they explode. Also, yes. So coming back to the question there by Scott about primordial black holes and Hawking radiation. So Hawking radiation is a process by which a black hole can kind of lose mass by emitting particles, and that's not a fair way of expressing it because nothing can escape from a black hole. A black hole is a region of space-time that is so dense that you'd have to be traveling faster than light in a vacuum to escape, and nothing to our knowledge can travel faster than light in a vacuum. This also means that if you're traveling at the speed of light and you shine a light, that light is still going to travel away from you at the same speed of light, which is cool. Just fun fact there. So yes, primordial black holes are black holes that are formed in the very early universe. And what can happen is on the event horizon, right on the point of no return around a black hole, you can create two particles, a particle and an antiparticle. This is something that happens very, very, very frequently in the universe. Normally, in the vacuum of the universe, you create a particle and antiparticle, they immediately annihilate, nothing happens, no net effects. But if this process happens right on the event horizon of a black hole, what can happen is that one particle falls in and one goes out. Just they're created right on the event horizon and they travel one into the black hole, one out. This means that they can't annihilate. So you've kind of borrowed energy from the vacuum of the universe to create these particles. And the way you give back this energy, because energy must be conserved, is the black hole loses a bit of mass. So in a sense, it gets smaller. This is a process that we think should happen. Then by the time the black holes reach a specific point, they are going to lose everything else they have in them. Then there's a question of what happens to all the information that fell into a black hole. Good question, we don't know. But in this case, as Scott was just saying here in the comments, any black hole, if it is to evaporate via Hawking radiation, will be small at the time. So it doesn't matter if it's a primordial black hole or a stellar black hole or even a supermassive black hole. If they reach the point where they've lost enough mass via Hawking evaporation that they actually explode, they would do this, they would produce a gamma ray burst, and the black hole would be a lot smaller at the time of actually doing this. Hope that answers the question. Just realized I needed to drink something. So going back to standard, what are the problems currently in cosmology? I mentioned dark matter, dark energy, big problem. We don't know what dark matter is. We don't know what dark energy is. So those are big, big unopened questions. What is dark matter? What is dark energy? But there are other open questions. And as we're on the topic, is this too slow for us to have seen any evaporation? Yes. Excellent comments here about primordial black holes. Also comment from Scott, that would the smaller ones evaporate faster? The rate at which you produce particles, let me get this right. Let me think about this. So if you can produce particles anywhere along the event horizon, the bigger the event horizon, the more surface you have on which you can have Hawking evaporation, the quicker the Hawking evaporation would be. So by that logic, I would say that the overall emission or loss of mass due to Hawking evaporation slows down over time. However, if you want to go from initial state to evaporation, then it's going to be a lot faster for a smaller black hole to do this because it has less overall mass to lose. So smaller black holes do evaporate faster in the sense that they're closer to the finishing line, but it's not related to the mass itself. It's just related to being smaller, starting from a smaller point. So then you have less mass overall to lose. Now, we have not yet seen Hawking evaporation in the universe. It's quite likely that the black holes that we have by the size, so the black holes that we know of in our universe are so massive that if they were to evaporate via Hawking radiation, it would take longer than the lifetime of the universe. And this is why we haven't seen stellar mass black holes evaporate yet. Then there's a question of if we had primordial black holes, could these have already evaporated? And in that case, the answer is potentially. There is some effort to see if we can actually relate the gamma ray bursts we have seen to evaporating primordial black holes. It's still not completely clear, probably not, but maybe. So in principle, we have not yet seen Hawking evaporation in the universe. We know that based on the mass of black holes that we've seen, or not seen, but that we've inferred the existence of, their evaporation time is longer than the current age of the universe, but primordial black holes could actually be evaporating today. So we could already have evaporating primordial black holes. And on the topic of black holes, of course, black holes are a region where space-time is very, very dense. There's something that is a gravitational effect. And gravity is another one of the big open questions in cosmology. Thank you for giving me that excellent segue there. So gravity is one of the biggest mysteries in cosmology and in physics in general. We have four forces in the universe. Everything we know interacts via some subset of these four forces. So the first force is the one we're all very used to, is electromagnetic force. Electricity, magnetism, light goes on, magnet sticks to fridge. It's something we can play about with. We have pretty good understanding of it. Then we have the strong nuclear force, which holds atoms together. It holds quarks together inside protons and neutrons. We have the weak force, the weaker nuclear force, which is responsible for radioactive decay and a lot of cool other things. And then we have gravity. I drop pen falls down. Earth stays in orbit around sun. Gravity. We have no idea what gravity is or how it works. Is gravity just curvature of space-time? Is it a force? We have a good theory to explain gravity, which is Einstein's general relativity, but gravity is still very mysterious. And then how do we fit gravity in with the other forces? We know that in the very, very early universe, the electromagnetic force and the weak force were joined. We think at some point the strong force was also joined together. We have no idea how gravity fits into this picture. We don't understand how gravity behaves on the quantum level. So that is another big mystery in cosmology currently, the nature of gravity. So the nature of gravity, dark matter, dark energy, these are questions. But these are, you could say, questions that cosmology has always been chasing. These are things that these are the big questions out there. But there's also currently some other questions that are perhaps weren't a thing 10, 15 years ago and are a thing now. One of my favorites in this regard is what is known as the cosmological tensions. It sounds very dramatic. So often in cosmology, there are several different ways you can go about measuring something. For an example, the expansion rate of the universe. So if you want to ask the question of how fast is the universe expanding, there are a couple of different ways you can try to answer this question. We know that the universe is currently expanding. We know that this expansion is accelerating. But how fast, or what is the rate of this expansion? This quantity, this rate of expansion, we call the Hubble constant. So if we have, I just got distracted here, Hubble constant, put a pin in that, because I saw proton decay in the comments and I like proton decay. So maybe in 10 to the 100 years, everything will be gone? Absolutely. There are so many ways the universe could end, so many ways everything could just blink out of existence. You know, proton decay is a thing that could happen if If protons decay, we think they don't, but if protons decay at some point, everything we know would just decay. We can have the vacuum death of the universe, the expanding bubble, like the vacuum decay, expanding bubble of death. The universe could basically blink out of existence now, and there's literally nothing we could do about it, and we would not see it coming. Fun. I'm not going to go into all of the core ways the universe can end. I've done streams about that. There's a very fun stream on the YouTube channel about that. I'll link to it. I always say I'll link to it, and I never link to it. But there is a stream on the YouTube channel for End of the Universe. And I'm not going to derail it too much because I will spend hours talking about that. Somehow I find it very fascinating to think of all the ways the universe could kill you. But coming back to the Hubble constant, thank you, David, for the reminder there. Hubble constant, expansion rate of the universe. And there are several different ways we can measure the Hubble constant or the expansion rate. One of the ways that I think is really cool is going back to my favorite thing, the cosmic microwave background radiation. This is a snapshot of the early universe. Now, when we measure things from the CMB, what we extract from the CMB is the standard cosmological model. So we find 6 main parameters, which are 2 parameters related to the initial conditions of the universe after inflation, the amount of dark matter, amount of dark energy, amount of normal matter, and the time at which stars turned on. These are the 6 parameters we need, the 6 numbers we need to explain a lot of stuff in the universe. And it's really cool that we can explain so much with these 6 numbers. 2 initial condition ones, amount of dark matter, amount of dark energy, amount of normal matter, and time at which stars turned on. That's it. That's all you need. And this is our standard cosmological model, which we call lambda CDM. Lambda for dark energy, CDM for dark matter, cold dark matter. And once you have these 6 parameters, you can calculate other things from them. And one thing you can calculate is the Hubble constant. But at this point, you're assuming that this set of 6 parameters is complete and it's all the information you need. And then you use these 6 parameters. You say, okay, assuming lambda CDM is correct, which I've just measured from the CMB, then what does this give us about the expansion rate of the universe? Never apologize for asking questions here, James. This is the point of the show. You can ask me anything. And if I derail the conversation, that's up to me. But please never apologize for asking questions here. This is the point of the show. You are all encouraged to ask me anything you want, even if it's off topic. If it's too off topic, I won't answer it. So feel free to ask away. So yeah, we can ask the CMB, what is the expansion rate of the universe? What is the Hubble constant? And if we do this, we get a value of 67.3. What we can also do is look at the stars that are exploding in our local neighborhood, not in the Milky Way itself, but in our local neighborhood. Stars that are exploding are supernovae. These are things that have a specific brightness. It's like holding a candle up and walking away. Based on how much light I'm receiving from the candle, I can know how far away this candle is. And if you use that, you can get a measurement of the expansion rate of the universe. And if you use supernovae, it's kind of like using something in the early universe, which is the CMB, and something now, which is supernovae. And you'd hope in a standard model of consistent cosmological model, you'd hope that asking this question different ways, you get the same answer. But what actually happens is from the CMB, you get 67.3 plus minus 0.5. And from the supernova, you get an answer of 74.0 plus minus 1. Which means these values are different. They're close. They're very, very, very close. You know, if one had been 60 and the other had been 10 million, we'd have a problem. But these values are close, but they're not quite close enough. They're what we call more than 5 sigma difference. This means it's no longer likely that it's a statistical fluctuation. And this is a problem. And this is what is known as the Hubble tension. It's a tension in different data sets. We have different data sets that are giving us different answers. This is not something we like. We want to get the same answer when we ask different data what is happening. In a consistent theory, the data should always give you the same answer, and here it doesn't. But it's close, which means we're not far off, but something somewhere has to change. And likewise, we have another tension, which is similar one when we look at how matter clusters or how matter clumps together on specific points in the universe. You can once again ask the CMB, as David Dunn is saying here. I do like asking things of the CMB, asking the CMB questions is what I do. And we can ask the CMB how much matter should cluster. And then we can also use what we call weak lensing experiments, which measure how distorted galaxies are And based on how distorted galaxies are, you can infer the object that is distorting the light from this galaxy. This is what we call gravitational lensing. And once you have that, you can get an idea of how matter clusters. Again, CMB is early universe, weak lensing experiments are current. And once again, you get a different answer. In this case, it's only about 3 sigma away, which is not as dramatic as 5 sigma, but it's substantial. Sigma just tells you how far apart things are, or your degree of belief in something. So, yeah, these are the cosmological tensions, the Hubble tension and what we call the S8 tension, which is just this clustering tension. So this is another big open question, and this is not such a fundamental one as the origin of gravity or something like that, or what is dark matter. It's like, is our standard model of cosmology correct? Is there something wrong? What could change our answer here? So this, to me, is one of the coolest questions, open questions in cosmology. And then, of course, we also have things like, how do neutron stars behave? What happens when neutron stars and black holes smash together? What are black holes doing? So there's a lot of open questions in cosmology and a lot of things that are interesting and that are worth answering. So that's just a broad overview of the current thing and what I like asking about the universe. Going back to the comments, if Mond is right there, what are all those maps of dark matter mapping? The thing is, if Mond is right, we can't explain the CMB. So Mond is modified Newtonian dynamics. It's an alternative to Newtonian gravity, which is embedded within Einstein's. It's one realization of Einstein's general relativity. Unmodified Newtonian dynamics is trying to explain dark matter or the effects that we attribute to dark matter without using dark matter. And Mond is very good at explaining one observation, but Mond cannot explain the CMB. So if Mond is right, then something else is fundamentally wrong in the universe or with our own understanding. Because if Mond is right, we have no idea how to explain the CMB. So then it's not just about mapping dark matter that's a problem. Then it's like, okay, everything needs restarting. But there's a lot more data supporting dark matter rather than Mond. Is one value or another of the Hubble constant better for different candidates of dark energy or dark matter? I love that question, Paul. That is an excellent question. So the reason I love that question is because that's a lot of what I've worked on. I have, I think, 4 or 5 papers asking exactly that question. And you can solve the Hubble tension somewhat with different models. For an example, if you have a specific type of dark matter that is massless, in addition to your massive dark matter, and we call this massless part like dark radiation because it's radiation in the dark sector. If you have dark radiation that interacts with dark matter in a specific way, you can solve the Hubble tension. But then you make the other tension worse. And then you're adding new parameters, you're fine-tuning it to get the answer that you want. But a lot of what I've done, a lot of my research has been asking this question of how much can we modify dark matter and dark energy or dark matter in general to try to explain the Hubble constant. And you can find different numbers. What we want to do, ideally, is here you say, okay, let's assume the value of 73 today from supernova is correct. Perhaps what went wrong is how we interpolate between the CMB and today. So tying this into James's question here of shouldn't we expect a different number because we're measuring at different points in the universe? That is an excellent point. That is an excellent question here, James. So when we measure the expansion rate from the CMB, we measure the expansion rate at the time of the CMB, and then we calculate what it should be today based on our understanding of the knowledge. So this is kind of fast forwarding 13.5 billion years based on everything we know of cosmology. So the fact that doing this, the numbers are so close is incredible. But they're still not close enough. So here we're saying, like, we take the CMB, we project it forward in time to what the expansion rate would look like today based on what we measure of the CMB. And then we compare it to what we're measuring today. So then, yes, we do expect it to be off at different times, but once we've done this prediction of going forward, this is when we expect it to be accurate or in agreement. And what we try to do when we try to solve the Hubble tension often is say, what needs to change in our interpolation between CMB times and today in order to get the right number today? And some ways you can do that is modifying dark matter and dark energy. you can also do things with like magnetic fields in the early universe. There's thousands of proposed solutions to the Hubble tension. A lot of them mean changing our standard model of cosmology. Some of them mean changing our understanding of supernova. Some of them are just saying like maybe the experiments are wrong. But we haven't yet found a convincing answer to all of these questions. What does 42 mean? Life, the universe, and everything. It is the ultimate answer. Is the universe really infinite or just really big? Universe is infinite. It is infinitely big. The observable universe is the patch of the universe that we have access to, and this is something that we can quantify, we can give a size to it. But the universe itself is an infinite concept. There is no boundary, there is no end to it. It is infinitely big and very, very fun. Okay, so current status of cosmology, we don't know what dark matter is, we don't know what dark energy is, we don't know what gravity is. I am by no means an expert on quantum gravity, so I'm not going to go into the differences between loop quantum gravity and string theory, whether you like your universe stringy or loopy. We don't know quantum gravity. We don't know how to solve the cosmological tensions properly. We don't yet understand compact objects like neutron stars and black holes as much as we want. So where do we go from here? What's happening in 2023? So there are several cool things happening in 2023, and a lot of them rely on existing experiments. So I want to go back to the question earlier of what are the best experiments to study dark energy and dark matter? And there are several different ones that we can think of. The first one I want to talk about, assuming my voice lasts. Yeah, there's an excellent point here by Paul, that when we say the universe is infinite, it means that even after the Big Bang, the universe was also infinite. Even though we say it was smaller than it is now, it was still infinite. Yes, you can have infinities that are smaller or bigger than other infinities. This is something you can do in maths, like this infinity is larger than this infinity. But yes, you can have one infinity being bigger than another infinity, and they're still just infinity. Okay, so first experiment I want to talk about is the dark energy survey. I don't know why I've suddenly started coughing. I've been fine all day until the stream. So, dark energy survey, this is a telescope that, as the name implies, is aiming to study dark energy. So it's a survey that took data already a few years ago. It has finished taking data. So it took data between 2013 and 2019. This is a telescope that is set up in Chile, and it is trying to measure the expansion rates of the universe and how matter evolves over time. So it's basically trying to create a map of the universe going back in time. Dark Energy Survey, as I said, finished taking data already a few years ago, and they are still releasing the data. We've had the Dark Energy Survey year 1, we've had the Dark Energy Survey year 3 results. At some point, we should get the next big dump of results from the Dark Energy Survey. They're trying to understand the nature of dark energy. It's not completely clear if there will be a new data release this year, in 2023, but maybe. I'm not completely sure when the next data release is, but if there is going to be a year 5 data release, it would be this year. So this is something that may or may not give us more data about dark energy within the next 12 months. Now, before we go on here, very quick question. Why doesn't the solar system expand if the whole universe is expanding? This is a great question, and it comes down to the battle between gravity and dark energy. So gravity is pulling everything together. As far as we know, dark energy is pushing everything outwards. On small scales, such as the solar system, gravity wins. But when you zoom out and you focus on large enough scales, dark energy wins. So gravity is very good at close by things, but once you zoom out and you consider that between us and the next galaxy is a lot of empty space, or between us and all the other galaxies is a lot of empty space, that's a lot of space for dark energy to push things, while gravity is mainly playing its role within the galaxies themselves. Within the galaxy, you have a lot of gravitational force that is holding things together. But once you step out, you have dark energy everywhere. So in spaces where you don't have big clumps of matter, such as the vacuum of space, dark energy wins the battle and the universe can expand. Next experiment I want to talk about is DESI, the Dark Energy Spectroscopic Instrument. This is one of my favorite telescopes. This is a really cool telescope that we have. And it's something that is starting to take data already. So the idea of this instrument is that it's going to, let me just check something here. I wonder if does my camera blink out sometimes? Let me know if my camera blinks out, because I'm curious if when I change application, the camera blinks out here, because I have a slide deck to help me with what I'm saying. And I'm wondering if when I open that, I lose my camera. Anyway, just let me know if my camera just blinked out there, because it does for me. There are no dumb questions, Scott. But why is Andromeda on a collision course with the Milky Way? Excellent question. And the answer to that is because it's close. It's relatively close in cosmological terms. It is the closest galaxy to the Milky Way. And galaxies that are close by within a local group can still feel a gravitational force between each other. It's really when you take the step back and look on large enough scales. Two galaxies are nothing on cosmic scales. So you can have galaxies that collide. We've seen galaxies collide. It's really when you take the step back that dark energy wins. So going back, let me bring up my image again. Going back to the Dark Energy Spectroscopic Survey, you can see the cool logo in the bottom left. I think they have a really cool logo, which is why I'm including their logos here. So the Dark Energy Spectroscopic Instrument is in Arizona. It started taking data in the end of 2021. It's a 5-year mission. It's going to observe 35 million galaxies and quasars. And what it's trying to do is create a 3D map of the universe. Now, the reason this is so cool is because the further out in the universe you look, the further back in time you're looking. If you can figure out how galaxies are distributed close by, you're looking at what is happening today. Thank you for confirming that the camera didn't turn off. It's odd because when I change application, my camera disappears. So I just assumed it was working. Thank you for confirming that. Then if you look further and further out into the universe, you're taking a snapshot of what what matter looked like back in time. Now, as we know that galaxies follow the underlying dark matter distribution, if you can map all of the galaxies around us, you get an idea of what dark matter is doing today. If you map all of the galaxies around us and going out into the universe, you get a map of what dark matter has been doing across different times, which then tells you also how matter has changed, which tells you how dark energy has been behaving. So DESI Dark Energy Spectroscopic Instrument is creating this 3D map of the sky to try to understand the nature of dark energy. And the very, very, very cool thing is they already released their first sky map. After a few months of taking data, they released this. This is part of this is one slice of their 3D sky map that they've already released. And this thing here is amazing. Every colored dot you can see here corresponds to a galaxy. And this is why I say that 2 galaxies is nothing. There are thousands of galaxies in this image, and this is just one slice of a 3D snapshot that DESI is constructing. They've released this image about 8 or 9 months ago, but they didn't release any physics analysis of it, just like, here's the pretty image, now we're doing science on it. It's very, very, very likely that there will be the first results from DESI this year. I'm not involved in DESI, this might not be the case, but based on when they release this first map, I'm expecting an update from DESI this year. They're not going to come and say, okay, we've changed the nature of dark matter. But what they might do is say, like, look, here's a new pretty map. And here's some data we've gotten out of this map. Here's some science results. I'm really hoping that there will be some preliminary DESI results already this year. So that's absolutely something to look forward to. And now I get to what is my favorite space telescope. And I'm very sorry for one reason, because this is not the experiment that should be my favorite, but it is my favorite. And this is the Euclid mission. Euclid mission is an incredible telescope that is set to launch this year in 2023. So the Euclid mission, this is an artistic representation, of course. The Euclid mission is a European Space Agency mission, and it is the most ambitious dark matter experiment and dark energy experiment that we sent to space, that we're going to send to space yet. To date, it is one of our most ambitious missions. It is going to measure the distance and the distance and the redshift of galaxies up to 10 billion years old. So it's going to peel back 10 billion years, and it's going to try to see how dark matter has behaved over 10 billion years of evolution and how dark energy has behaved over 10 billion years of evolution. Euclid is considered to be one of the best tests yet we have of the standard cosmological paradigm. Euclid could make or break our standard model of cosmology. When we get the data from Euclid, we might look at the data and say, like, haha, dark matter, dark energy behave exactly as we expected them to across 10 billion years of evolution. Or we might get the data from Euclid and go, we have to rethink everything we know about dark matter and dark energy. It is the make or break of the standard model of cosmology. And it is launching in 2023. So I first heard about Euclid when I was in my undergrad. And I remember hearing about it and thinking, this is insanely amazing. This is such a cool telescope. I cannot wait to get the data from Euclid. It's going to be so fun. It is the telescope, one of the two telescopes I'm looking forward to the most. The other one is, of course, LISA, the Laser Interferometry Space Antenna, which is hoping to measure primordial gravitational waves, but that's 10, 12 years away. Euclid is happening this year. Euclid was supposed to launch initially in February, but due to the ongoing war in Europe, it got delayed. But it's found a new rocket to launch on. It is scheduled to launch in autumn 2023. So if all goes to plan, within the next 9 to 10 months, Euclid will fly. I am going to be an absolute mess on the launch day. I'm not going to be live streaming my reactions to it. I'm just going to be quietly watching and hoping for the best, because rocket science is difficult. And Euclid is going to give us such amazing data. I cannot wait to see what is happening with Euclid, and it launches this year. Big Rip implies that the expansion of the universe would pull apart matter on the fundamental level. That is correct. Yes, Big Rip is the expansion rate of the universe gets so strong that it basically increases in strength. It can beat gravity and pull everything apart at the atomic level. Wondered why the picture was so fuzzy, then I remembered that I had the quality all the way down. Well, I'm glad that's not on my end. Off topic, is data from these telescopes proprietary? Who determines who gets the data? This is an excellent question. Now, what often happens with these telescopes is that the data is made public after a certain time. There's a lot of scientists who have put a lot of work into these telescopes, and usually there's a shortish embargo of 1 or 2 years, where the people who have been involved in the mission get to play about with the data for 1 or 2 years, and then it's made publicly available. It very much depends. Each experiment has different rules. Depends if it's NASA, if it's ESA who's funding it, there's different rules. But usually the people involved in the mission get to use the data first for a few months or a year, but then it is made public. Most telescopes do, or most experiments do make their data public at some point. Not all of them. There are a few notable exceptions. Not pointing at anyone, Dama, here, but yes, there are a few notable exceptions. But usually this data is made public after a certain amount of time. You give 1 or 2 years to the people who have spent 20 years of their life working on this mission to get first rights, and then the data is usually made public. So there's an excellent question here by Paul of why do these matter if the JWST and Hubble are up out in the atmosphere? Are they different or better in other ways? So they're very different in terms of science goals. So the Hubble Space Telescope is mainly looking within the visual range. JWST is looking in infrared. So they're looking at things that are close by using the electromagnetic spectrum. What Euclid is going to do is it's going to map the distribution of matter. So not so much, here's a pretty galaxy, which is what Hubble and JWST can do. They're doing amazing things, like JWST is looking at the atmospheres of exoplanets, but it's much more focused on smaller things. Whereas what Euclid is trying to do is look at the overall cosmos, not so much what this star is doing or what this planet is doing or pretty pillars of creation, which are amazing images and give us a lot of science. I'm in no way taking away from that. But this is really trying to map how the large-scale structure of the universe, this cosmic web, has changed over the course of time. So its science goals are very, very different. Euclid is looking at dark matter and dark energy. JWST and Hubble won't tell us much about dark matter or dark energy. They'll tell us a lot about cool other things, but they won't tell us much about dark matter or dark energy. So they're neither better nor worse, they're just different. They're looking at different things, different experiments for different objectives. Okay, so I've covered DES, which may or may not give us results this year. DESI, which I'm hopeful will give us results this year. Euclid, launching in autumn. And I have one more dark matter / dark energy experiment I want to talk about, which is the Vera-Rubin Observatory, formerly known as the LSST, the Large Synoptic Survey Telescope. It was renamed to the Vera C. Rubin Observatory. It is in Chile as well. It will have an 8.5 meter primary mirror, and it is also set to measure. It is also set to measure the overall distribution of matter throughout time. And this one, if all goes to plan, the first light. So what we say about first light is the first time you turn the telescope on to make sure that it's getting data. It's not doing any science, it's just a milestone of, look, everything is working. And you usually do first light for different parts of the experiment. So the Vera-Rubin Observatory is a dark matter telescope as well. It is really going to help us understand what dark matter is doing today. So a lot of the other ones are looking at dark matter throughout time. Vera-Rubin Observatory is looking at what dark matter is doing today. And also a bit about what it's been doing throughout time, but it's also really set to shape our understanding of dark matter. The first light for Vera-Rubin, for part of the Vera-Rubin experiment, is December 2023. So within 12 months, if all goes to plan, one of the instruments on Vera-Rubin will get its first light. Then over the next few months, they'll do the first light on the other instruments, and it will start taking data in 2024. But the first light is a big milestone, and first light for Vera-Rubin is 2023. So that's cool. That is something that is interesting and exciting. And even though it's not a result that we're going to get, it is something that is happening, and it's the next step towards the Vera-Rubin Observatory, named after Vera-Rubin, who was a pioneer in researching dark matter. It's a next step in making Vera-Rubin Observatory a reality. Is Euclid related to the S8 tension? So I mentioned before we have this clustering parameter, and this is an excellent question here. So Euclid will measure how matter clusters on different scales. And from there, we can calculate a value of sigma 8 of S8. So it won't be a direct measurement of S8, but it will give us a new number for S8. So it is giving us a new data point here that we can use to get the strength of the clustering. So I call it the strength of the clustering. What I mean by this is how much dark matter clusters on scales of 8 megaparsec. So you take 8 megaparsecs, it's a specific length scale in the universe, and you see on this specific scale how much does dark matter clump together. And this is related to the amount of matter you have, so it's related to the amount of matter and to how matter is distributed. Euclid will give us another data point to try to understand S8. Speaking of JWST, is the Lagrange point past the moon's orbit? I would assume so, otherwise it would be perturbed. Yeah, the Lagrange points are ones that are quite far away from Earth, and they're stable points where you can put a telescope there and not really spend much energy. It's a stable orbit point between the Earth and the Sun. So any two body systems, such as Earth and Sun, have 5 Lagrange points. If you consider this is this is the Sun, this is Earth, there's going to be 5 Lagrange points. One is here, one is here, one is here, one is in between, and one is the other side.
So you have 5 Lagrange points, and usually if you dump a telescope in a Lagrange point, it's very easy for it to maintain orbit. So it's a convenient thing to do. Okay, another big thing happening before I move on to the other big thing. To recap here, what I said is that dark energy survey might give us new results. The dark energy spectroscopic instrument will probably give us new results this year. Euclid will launch this year, or will attempt to. Vera Rubin Observatory will get first light this year. Now, all 4 of these could shed light on the nature of dark matter and dark energy. This means that they could also potentially help us address the Hubble tension. They could potentially help us understand the sigma 8 tension, the SA tension. And depending on their results, they might help us address the question of what is dark matter, what is dark energy. So these are experiments that are looking these are experiments that are really looking to move cosmology forward. The data and the results we get from these experiments are pushing our understanding of dark matter and dark energy. They might help us address sigma 8 and the S8 clustering tension and the expansion rate of the universe tension. So yeah, when we talk about Lagrange points, it's Lagrange points between the sun and the Earth. There are also Lagrange points between the Earth and the Moon, but we don't use those. It's the ones between the sun and the Earth that we care about. So these are experiments that are either giving us new data or reaching important milestones this year. There are also several weak lensing experiments that might give us new data, and there are several CMB missions that might give us new data. All of these are things that could push our understanding of the Hubble tension, the sigma 8 tension, the nature of dark matter, the nature of dark energy. So these are all really, really, really cool things that are going to happen this year. I'm not saying we're going to understand all of these things this year, but we might get one step closer to understanding these things, or we might push our knowledge a bit more. All of this so far has been focused on dark matter, dark energy, and the cosmological tensions. Of course, as we already discussed, now we have the JWST, which is pushing our understanding of how galaxies form and the nature of exoplanets, planets outside our solar system. JWST has been up and running or launched a year ago. It has already given us amazing pictures, amazing data, and some amazing results. So it is likely to give us much more in the coming year. And there is one more thing to look forward to this year in cosmology, and this is changing gears and going back to gravity and compact objects. There are several different, there are some ongoing experiments looking for gravitational waves. Gravitational waves are ripples in the fabric of space-time created by dramatic things such as black holes smashing together, or neutron stars smashing together, or even dramatic events in the early universe, like the initial inflation expansion of the universe could have produced primordial gravitational waves. If you have strange things happening in the early universe, you could have bubbles that produce gravitational waves. There's a lot of things that produce gravitational waves. I'm not going to go into a whole 1 hour explanation about gravitational waves now. I'll link to the video. But one of the experiment that found the first direct proof of gravitational waves is LIGO. LIGO is one of our ground-based observatories looking for gravitational waves. We have its companions Virgo, we have Cagra. All of these are ground-based gravitational wave experiments trying to understand the nature of black holes, of neutron stars, and all of these cool things. And LIGO has been down for the last 2 years for upgrades. After 2 years of upgrades, it is ready to be switched on again. In March this year, is it March? Let me just check. Yes, in March this year, observing run 4 of LIGO is starting. In the first 3 observing runs, we got 103 by now, measurements of events of either black holes smashing together or neutron stars smashing together, or even black holes and neutron stars smashing together. We have got amazing data from LIGO already, and now it's been upgraded. Now it's LIGO, this time we mean business. LIGO Observing Run 4 starts in March with an improved version of LIGO. March is like 2 months away. That's nothing. So that is going to be very exciting, because the more we learn about gravitational waves, the more we learn about gravity itself. So it is a really, really interesting thing to pay attention to. And it's something that we really can expect more data on very, very, very soon. And I cannot wait. So to recap, what's to look forward to in 2023? Maybe results from Dark Energy Survey, probably results from Dark Energy Spectroscopic Instrument, launch of Euclid in autumn, first light for Vera Rubin Observatory at some point in December. LIGO Observing Run 4 is starting in March. JWST is going to give us some amazing science, and we might get more data from CMB missions and from weak lensing missions. So we might understand more about dark energy, about dark matter, about the cosmological tensions, about gravitational waves. There is a lot happening. There is a lot to look forward to. I cannot wait to see what results I haven't even considered that are coming out this year. You know, this is the stuff that I know about. Maybe I wake up tomorrow and there's a new science paper that changes everything. That can happen. And this is why it's so fun being a scientist, because all of these things are things that we know to expect this year. And then there's all the unknowns that are going to happen that will shape everything again. And I think if you can take one comment away from this, it's that we are really at a good time for cosmology. We're at a time where we're starting to get really cool data from really cool experiments. We've had a lot of data and different experiments. I think the next 10 years, the next decade, is going to completely shape our standard cosmological model. Within the next 10 years, I think we're going to push our understanding of dark matter and dark energy beyond what we have now. And anytime we get any of these new results, you can come to Cup of Cosmology to hear about it. Anytime there's anything new to chat about in cosmology, Sundays, 8 p.m., 7 p.m. in Europe, with time zones weird. Cup of Cosmology will be here to bring you the latest news in cosmology with fun guests, fun topics, and now I feel like I'm doing an ad for my show, so I'm stopping that there. And there was a comment here by James of a wall-sized chart of every active planned telescope probe's experiment in space would be great. And I agree, and such a thing does exist. There are two versions. This is the ESA one, the European Space Agency one. This is an actual poster you can get, and I actually have this poster. This is slightly out of date, but you can see here across the electromagnetic spectrum the different experiments that we have. This is quite a few years out of date by now, but you can see Euclid here, you can see the JWST, and there is a similar one for NASA, which is this one here. And you can see different experiments, both ground-based and space-based. This is NASA-based. So this is something that does exist, and you can find the posters online. So if you want to find them, you can. And I actually have one of them. I'm going to put it up at some point. I rotate the poster behind me, and at some point you'll see the ESA fleet appear behind me. Until I get a LISA-specific poster, because then LISA-specific poster will go up. I do actually have a CMB poster that I haven't put up yet, so maybe that should come back at some point soon. As Paul is saying, another thing to look forward to is new and returning guests on Cup of Cosmology. Yes, I have a long list of people I'm going to message like, hey, new year, Cup of Cosmology. And I have a couple of people who have asked to come back. So there's going to be more guests, there's going to be more topics. As always, if there's somebody you want me to bring on the show, message me and I will try to make it happen. I can't guarantee that I can get anyone, but I will try my best to get people on the show and to bring you all the new topics. So cosmology is an ongoing and active field. There's a lot of cool stuff to be done. There's a lot of cool stuff to look forward to this year, including the launch of Euclid and the new data from LIGO, gravitational waves, dark matter, some of my favorite things. This is going to be a fun year for cosmology. Okay, spoke for an hour and 5 minutes today. Thank you everyone for joining. It's always so nice to see so many of you come and ask fun questions and keep the conversation going. And I love seeing you chat among yourselves as well and answer each other's questions. That's really cool. So thank you everyone for being here. This has been, as always, great fun. Please do subscribe, comment, like the video, use your YouTube stuff. Cup of Cosmology will be back next Sunday, same time as today. That's 7 p.m. Central European Time, 1 p.m. if you're on the East Coast of the US, 10 a.m. if you're on the west coast of the US. There is a time zone converter on cosmology.com, so you never miss a show. And if you follow me on either Twitter, Mastodon, or a post, you will always get a notification. I will always put up a post a few days in advance advertising the streams. So whichever social media platform you feel like following me on, there will always be Cup of Cosmology updates. And yes, I am on Mastodon. I'm not going to go there. Thank you, everyone, for joining. This has been great fun. I hope to see you next Sunday. And in the meantime, I hope everyone stays safe and you all take care of each other.